welcome back to the Advanced Linear Algebra. So what we will do in today's discussion, we will move towards some of the basic theory of the unitary matrices. So we'll talk about unitary matrices in detail. In particular, we will talk about isometries, particular kind of linear transformations and their relationship with the unitary matrices. Then we'll talk about some of the basic properties of the unitary matrices, and then probably I'll quickly talk about the permutation matrices, okay, and probably I'll then talk about the QR factorization, of the matrices, okay, of the matrices, say entries from the complex numbers, and then we will kind of move towards the the theory of orthogonal projections. So kind of we will start with what do we mean by the orthogonal perps. Okay, so we will start with orthogonal perps, and then we'll move towards the orthogonal projections, and then we'll also talk about that how they are related with the stuff that we, say for example, covered previously, especially about the unitary matrices. And then we will talk about some of the applications of the orthogonal projections and the orthogonal perps actually. So pretty long agenda, so we will carry on our discussion on all of these topics, and probably we will cover most of this stuff today. Okay, so let's start with say isometries. So we all know that linear transformations can be interpreted in many different ways actually. So for example, if you have, so think about the rigid motion of a chalk actually. So take this chalk, okay, and carefully look at it. So if I am translating this chalk, so taking it from one position to another position in space, okay, so what is happening is that if you look at any 2 points on this chalk, or any 2 parts of this chalk, the distance between them, those points on the chalk, is always same actually. So that distance is not changing when you are doing a translation actually. The same would be true if I, for example, do the rotations, okay. So if I do the rotations, distance between any 2 points on the chalk would stay same. Or I can do what you call a combination of translation and rotation, okay. So I'm like, okay, translating and rotating simultaneously, still what do you call the distance between any 2 points would not, what do you call, change actually. This is not true, for example, when a person is moving actually. So when I am moving, the distance between the different parts, because my body is flexible, is changing at all the time, okay. For example, if you are talking about a rigid vehicle, okay, so the car is moving, so you take any 2 parts or the points of the car, for example, and measure the distance while it is at rest and while it is moving, no matter how it is moving. So it's like moving forward or in circles or taking a turn, the distance between the 2 points of the car is not going to change. So all these motions are what you call rigid motions. So the transformations the transformations under which the distance between 2 points is preserved actually. Okay, before the transformation and after the transformation, you call such maps as isometries. Okay, so isometries are the distance preserving maps, they are the size preserving map actually. Okay, so for example, if I am making a translation or rotation, the size of the chalk is not changing actually. Okay, so that's an isometries. So isometries are a pretty important topic, from different perspectives, especially they play a very interesting role when you are studying, say for example, mechanics of the rigid objects actually. Alright, so I'm going to start with isometries on inner product spaces actually. So I'll define isometries on inner product space. I'm going to always consider in this lecture by V, calligraphic V is going to be an inner product space over a field F actually, and this field may be R, or it could be the set of complex numbers actually. So this is fixed for our upcoming set of discussion, probably for the entire lecture actually. So let's define that what do we mean by a transformation. So a linear transformation, okay, T from the inner product space to itself, okay, from the inner product space to itself, we're going to call this linear transformation is called isometry, okay, if it is a size preserving map actually. So what do you mean by size preserving map? So consider a vector u from V, okay, calligraphic V, and transform it under this transformation. And you compute the size of the u by computing the norm of it, and you compute the size of the transformed u, tu. It turns out their sizes are equal. Okay, might be changed, but their magnitude is not changing. The size of the vector is not changing actually. So this is true. If this is true for all calligraphic V, so you're going to say that your transformation is a linear transformation. So what is an isometry? So isometry is a size preserving map. It's a magnitude preserving map actually. So under which, if you take a vector and compute its magnitude and transform that vector and compute its magnitude, it turns out the magnitude of the vector is not changed actually. Okay? So this is what is really the size preserving map actually. For example, let's do some examples of it. Okay, so the first thing that I would like to talk about is about what do you call the complex rotations. Okay, so if I take, for example, field to be the space of complex numbers and nu be in an inner product space, then we define, say, T as a map that takes that from obviously V into V, okay, that swallows a vector u from complex vector in the product space u, and it gives you and spits out, say, a vector e to the iota theta u actually. So we can also interpret e to the iota theta u as kind of translating the vector u by angle theta, actually not translating but the rotating the vector u by the angle theta. And my claim is that this is an isometry. Why this is an isometry? So if you compute, for example, the magnitude of u, it turns out that this is equal to the e to the iota theta u. E to the iota theta is like a number actually, so you can pull it out and you're going to get what you call e to the iota theta times the norm of the u actually, and which would be equal to. So we know that e to the iota theta, magnitude of e to the iota theta is equal to 1. Why it is 1? I mean, if you remember, e to the iota theta is cos theta plus e to the iota sine theta, and if you compute, say, since the magnitude of cos theta plus iota sine theta, okay, so this would be equal to 1 actually. So what does this shows? That the norm of u is equal to the 1. So the complex rotations are is an example of what we call isometry. Let's talk about, say, another example. Let's talk about, say, an infinite dimensional space in which you have finitely many zeros. Okay. So you can see that the collection of vectors v1, v2, vn, so on and so forth, where finitely many of vi's, okay, are non-zero, in other words, that it's a collection of the vectors in which you have infinite tuple, but in each tuple only finite number of the components are what do you call non-zero, and the rest are zero actually. So the finite component can be anywhere, okay, and obviously these vi's can also be taken as are the elements from the field actually. So for example, one of the example in this in a product in this space is going to be, say, 1 0 0 0 0, or you can have a 0 2 1 0 0 0, so on and so forth actually. Then we know that this becomes a vector space, and you can also define an inner product on it, and it becomes what we call an inner product space as well actually. So I'm not getting into the detail that, you know, how you can show that this is an inner product space, like we talked about it when we were doing our chapter on our discussion on inner product spaces, so you can refer to that. Now let me define a translation, a transformation. Okay, so let me define the transformation V from V to V, calligraphic V to V, and the transformation goes like this. It swallows, say, a vector V1, V2, V3, and so on and so forth, and like this is an element in V, calligraphic V, and then just shift it. Okay, so this T is a kind of a shift transformation. So it shifts the entire vector to one point ahead. In other words, this V1 takes place of the V2, okay, and the place of V1 is what you call 0. The place of V1 is 0, and V2, and so on and so forth. So you call this as a shift operator, that the entire vector is being shifted. You know, each component is being shifted to the next position, and the first empty position you fill it with 0. So you call this as, what do you call, the shift operator. Okay. Now, what would be the norm of T of V1, V2, so on and so forth? So this would be equal to norm of 0, V1, V2, so on and so forth. And the norm of it is going to be really, what do you call, analog of 2 norm. So it's going to be, okay, take all of the finitely many vectors. For example, this is going to be the sum of absolute of 0 square, or the magnitude of 0 square, or v1 square plus v2 square, and so on and so forth. Okay, but this is same as the magnitude or the norm of v1, v2, and v3 actually. Okay, this is same as the norm of v1, v2, v3, because if you compute the magnitude of this is going to be equal to what do you call v1 square plus v2 square plus v3 square. Keep in view, this is not an infinite series. Okay, so in this the only finite number of terms are non-zero and rest are zero actually, so it's a finite sum. So in other words, by doing a shift in a vector, you can also do this in, for example, in finite dimension. Okay, by doing a shift in a vector, you do not really change the size of that vector actually. Okay, and the shift example becomes an example of an isometry. Okay, what are, say, for example, some of the basic properties of the isometries? You can do more isometries, as I said, that translation and rotations, we'll talk in a minute about it, that they are also isometries actually. Let me write the theorem, okay, which lists some of the basic properties of what you call isometry. So it says that let S and T be isometries. So these are isometries on V. Okay, so they are isometries from V to V. Then the composition of S and T is also isometry. Okay, so the composing one isometry with another isometry is an isometry. In other words, you know, the translation is an isometry, rotation is an isometry, but if you do the composition, in other words, doing the translation and then rotation, or rotation and then translation, that would be still an isometry actually. Okay, so T is an isometry. If T is an isometry, then T is a 1-1 map actually. Okay? All isometries are 1-1 maps, or 1-to-1 maps. And the third interesting property of it, that if V is finite dimensional, okay, this is true in finite dimension, and T is an isometry, then T inverse is an also isometry. Then okay, you can say that an isometry is invertible. Okay, invertible, and T inverse is also isometry. Okay, so you have two isometries, compose them, still an isometry. Isometry is a 1-1 map. Okay, so it does not changes the sizes of the sets actually. And if V is a finite dimensional vector space, T is going to be invertible, and T inverse, the inverse of it is also going to be the isometry actually. Okay. So these are some of the basic properties that, for example, I would like to quickly prove. So how can I show that ST is an isometry? Let's apply ST onto what do you call U and see what happens. Now S composition T operated onto U, I can write this as S operated onto the vector du. Okay, but I know that S is an isometry, so it does not changes the size of tu, so it would be equal to what do you call tu. And now since T is an isometry, this is equal to norm of U. So this shows that, you know, T is an isometric, as composition of isometry is an isometric. How can I show that T is 1, 1? We know, okay, so if I say, all right, so you might have seen an interesting result actually, which says that a linear transformation is 1, 1. Any linear transformation is 1, 1 if and only if its kernel is trivial actually. Okay, so what you can show is that its kernel is what you call trivial. So if I can show that for a given isometry, the kernel of the isometry is trivial, that would show that the T is the isometry is a 1, 1 map actually. So let's take U from the kernel of the transformation T or the isometry tree. Then we know that the T of U is 0. Okay? The T of U is 0. So I need to show that this U should also be 0. Why it should be 0? Think about it. If the T of U is 0, that means that the magnitude of T of U is equal to the number 0. So this is 0 vector, and this is number 0. But since T is an isometry, so the magnitude of TU must be equal to the magnitude of U. So this shows that the magnitude of the vector U is 0. Now can you tell me a vector whose magnitude is what do you call 0? So this is 0 if and only if U is 0. Okay, this implies that this is 0 if and only if U is 0. So what we showed, that I picked a vector from the kernel of T and I showed that it's 0, and this shows that the kernel of T consists of only 0 vector, so the T must be a 1, 1 map actually. So that's really the second part. You know, you might also remember a property, if not, I would say that, think about it for yourself actually, that if you have a linear transformation, and you know about that linear transformation that it is 1, 1, then that linear transformation, and you're like it's on a finite dimensional vector space, then that linear transformation must also be onto actually. Okay? So you can't have a linear transformation that is only 1, 1. Okay? Every linear transformation that is 1, 1 must be an onto linear transformation actually. Okay? Especially in a finite dimension actually. So maybe this is something for you to verify or recall, since this is the second course on linear algebra. Okay, so I'm going to assume some of the basic things you did in your first semester, first linear algebra course actually. So verify that if T is a linear transformation plus 1, 1, if then T is onto as well actually. Okay, T is onto as well. And and this will be true when the V is finite dimension. Now if T is a linear transformation and it's 1, 1 and onto, that means that T must be a bijection. And if it is a bijection, T is invertible. Okay? Then it is invertible. The only thing that I need to, so I can say, so I would say that T is invertible. Okay? That is that T inverse exists. The only thing that I need to show now is that T inverse is an isometry. Okay. So in order to show T inverse in isometry, I need to apply T inverse onto what we will call U. Okay. Now as T is onto, T inverse would also be onto, so you can say that T inverse of U must be equal to a V actually. Okay, it must be equal to a vector V in the space V. Okay, and you can also say that okay, U can be seen. So V is the image of under the T inverse R. V can also be seen as a pre-image for what do you call U actually. In other words, if the T inverse of U is V, then U can be seen as what do you call T of V. Okay, U can be seen as T of V. So if this is the case, then I can write this T inverse V as